good afternoon, and welcome to the final Masterly webinar. I'm Elena Minishi. I work in CRIT, and as partner in the Masterly project, we are responsible for communication, dissemination, and exploitation purposes. So we helped organize today's webinar. Now, without stealing too much time to our speaker, this is the agenda. After me, we will give our coordinator will give a very brief introduction of our Masterly project, and then we will dive into the technology that we developed. Thank you to the Masterly project. We will go through all three main use cases and the technology behind them, and we will give a more in-depth let's say a focus on with our last two presentations on two particular technology that were researched and developed to be integrated in our use cases. So now, without stealing much time to Apostolis Papavasileou from LMS, who is also the coordinator of the Masterly project, I will give him the floor for the introduction on the Masterly project.
Thank you very much, Elena, for the kind introduction. I hope now it is visible for everyone. And many thanks also to all participants that would like also to spend their time here today with us. This is the final webinar of the project, so we really hope that we have some interesting material for you, some material that can be of added value, especially for industry and manufacturing. My name is Apostolis Papavasiliou. I'm a project manager in Laboratory for Manufacturing System and Automation. We are a laboratory in the University of Patras in Western Greece, and we are coordinating this quite interesting project Masterly. Masterly is a project that has been initiated back in January 2023. So we had roughly 3.5 years to allocate for the developments and the research activities of this project. We are a rather large consortium, I would say, in the sense that we have 16 different partners from 7 different countries. We have quite of expert, let's say, consortium, both from a technical point of view, but also 3 core industrial cases. One is from Kleman in Greece, in elevators manufacturing. The second one is from Spain, from Aronova, the aeronautics production. And then we have also, of course, Decathlon from Italy on the sportswear manufacturing. Perhaps before going into detail in the project developments, it is worth also to mention what is the motivation behind the project, what especially is the challenge that we had to face when we started and initiated these development activities. So back then, what we have noticed is that in the current production practices, we had a lot of challenges in terms of customization. Industries mentioned a lot the issue of diversity of parts and products, in the sense that they had both parts and material of different kind of types or different sizes or different shapes. And this also was combined with quite a lot of changes in production and quite frequent product changes. This was also quite evident during the pandemic crisis back then, where we had quite a lot of short life cycles, and we have to provide technologies to enable, let's say, this kind of reconfiguration of the workstation. In other cases, we also had some problems or some aspects of small batch and high mix production, meaning that we also had to efficiently handle different kind of orders. You can see also some examples in the bottom side, like batches of thin parts, like battery packs. In other sense, we had also large and high payload parts, like these parts from aeronautics production. And also, and most challenging one, we also had industries trying to handle and manipulate parts with complex shapes and material, like the flexible materials we can see, like this HMI screen, for example. So based on this motivation, we also started envisioning and development the main components of the project. You can see that we have some core components in Masterly. The first one is oriented towards the intelligent workpiece handling. So here we have the modules that are related to the actual handling of the parts, like for example, autonomous mobile manipulators from our partners, grippers that are dexterous enough and enabled through the use of artificial intelligence in order to manipulate correctly and accurately the parts. And secondly, we had also to spend a lot of efforts integrating this AI-driven control of the project, in the sense that apart from the handling aspect, we had to provide to the robot the skills in order to perceive not only the environment or the process, but also the operators that are involved in this kind of applications. So that's why we have machine vision technologies with deep learning. We have digital twins that can track and replicate in real time what is happening in the physical shop floor. And of course, we have also the mechanism that is responsible for the decision making of the project, for allocating dynamically the tasks to the different resources. Third one, we have a core component about user-friendly interfaces. So this was a specific need from the industry, in the sense that in many cases we had operators involved in the current processes. So Masterly is a project that we have human centricity by design in the development of our modules. Here we have a lot of different examples. One is the AR-based interfaces providing instructions to the operators. We had also other kind of interfaces like smartwatch or tablets. So we experimented a lot in the different aspects of technology and how to interact with the robots or the machines involved in the cases. And last but not least, we also had to cover the aspect of interoperability. That's why we have as a core, let's say, orchestrator in the project, the workflow controller. This is how we call it. It is a central orchestrator providing interoperable interfaces based on ROS2. So it is, I would say, a state-of-the-art platform that can support also the integration of other kind of interfaces or modules if needed. So apart from these core components, I think it is worth just to highlight here some main AI enablers in the project in Masterly. So this is an example from elevators manufacturing we will see later on. We have dynamic handling with this dexterous gripper of smaller parts, rigid parts in elevators panels. We have pose estimation on the fly, meaning that we can track the exact orientation of the part while this is being handled by the gripper. And we have a lot of technologies that are oriented on machine vision. So we calculate dynamically the grasping points, even if the parts are occluded, like in bin picking applications. And we are also able to provide real-time collision-free picking for the robots in industry. In the right-hand side, we also have some aspects covered related to human action recognition. So it is not just providing instructions like it is currently done in the state of the art, but in Masterly, we are also able to dynamically track the performance and what is happening from operator side. So this is eventually quite helpful in the sense that you can also provide corrective actions to the operator. We have, as I mentioned, 3 pilot cases. One of which is a key exploitable result for Masterly. The first one is by Clement, the elevators manufacturing. So here we have a hybrid human-robot collaborative workstation. We have a lot of different part diversities, circuit breakers or switches, let's say, that the operator should assemble in the electrical panel. And in Masterly, this is happening in parallel between a robot and the operator to save a lot of production time. And it is integrated with AI-driven grasping point estimation and pose calculation for the correct grasping of the beam picking. And in parallel, we provide this kind of interfaces to the operator as we explained. Secondly, we have also the decathlon case, the sportswear production. So here we have also a lot of focus on challenging materials like flexible parts. And there is, as you can imagine, there is a quite diversity of parts in this huge company. So it is also quite a lot of challenging, let's say, to develop solutions to perceive the environment in the process. And we managed to have also our machine vision solution here combined with digital twin activities. Finally, we have also Aeronova, a quite huge company in the field of aeronautics. This is also a quite interesting case in the sense that we have quite high payload parts. So the aspects of quality and accuracy and reliability here is, I would say, quite important. In Masterly here we have a smart crane for autonomous transportation of these huge parts. In aeronautics we have also anti-swinging and collision avoidance technologies from our partners, and this is also combined again with the dynamic estimation of grasping points. So it is a quite tight and accurate activity in this operation. I think that was all as a brief introduction in the project. This is just our contact information for later on communication. From my side, I would like again to thank you for joining, and I think I will give the floor now to the next presenter so you can also have some more technical point of view of the project results.
Good afternoon, everyone. I hope you are able to see my screen. So my name is Francesca Canale. I'm a senior project engineer in SAM. And today I am presenting the key exploitable result number 1, which is the robotic cell for flexible material handling. So the scenario that we have addressed deals with the order preparation process for B2B and B2C in a typical warehouse environment. And in particular, we have taken as reference the decathlon logistics workflow. At the moment, this process is mainly performed manually by decathlon operators who walk into the warehouse with carts like the one you can see in this picture, and they are manually picking items from the boxes and placing them into the order box. The needs that Decathlon identified for this scenario were the automation of the picking operations, mainly to improve worker satisfaction, since this kind of operation are often repetitive and quite exhausting for operators who may have to walk several kilometers per day working in the warehouse. But of course, also the need of increasing productivity by passing from a baseline of 4 manual picks per minute to 6 picks per minute by a robotic cell. To address these needs, we have designed in Masterly a new scenario. You can see here in this drawing. This is the robotic set that we have designed. The main components are a collaborative robotic arm, which moves, and a modular gripper, which is responsible for picking the different products of the Decathlon catalog. We have also a conveyor system responsible for moving Decathlon boxes to the different stations of the cell, and also 2 different vision systems, one for looking at the box labels and a second one for looking inside the boxes to see the items to be grasped. We have also a manual station where the operator can perform the manual operation using a tablet, and this scenario has been designed to be collaborative, so the operator can work alongside the robot. About the challenges that we have encountered, the first one has been the high variability of products that Decathlon has in its warehouse. We are talking about 100,000 of different products, which may differ from for materials, dimension, weight, packaging conditions. To address this, we have defined 6 different categories of products which have similar properties, and we have defined a different picking strategy for each category. Also, IIT has designed a gripper which allows different grasping modalities to be able to grasp a different kind of products. Another challenge has been the synchronization of the whole system to avoid bottleneck. And to address this, we have designed a conveyor system which allow to move boxes along different routes to handle boxes that need different operations. These are some pictures of the robotic cell that we have integrated at the Decathlon logistic facility in Maddaloni, which is in the south of Italy. Okay, so in this slide, you can see an overview of the operations that we have in this use case and of the hardware and the software masterly modules that we have integrated. In the picture, you can see an overview of the conveyor system seen from above. The orange arrows indicates where the boxes are put on the belt and where they exit from the belt. And we have identified 3 main operating stations. We have as B the barcode station, as R the robotic station, and as M the manual station. So mainly the barcode station is the first one, is where the boxes are identified by reading the article numbers, and we do this thanks to the vision-based object geometry estimation developed by the University of Kiev. Then in the manual station, we perform the manual activities, so the activities where the operator is needed, and we do this thanks to the smart interfaces for human production interaction tablet interface developed by LMS. And then there is the robotic station, which is our main station of robotics activities, where we have the grasping point computation, again developed by the University of Kiev. Then we have a collaborative robotic arm provided by Comau, a modular gripper for flexible materials designed and provided by IIT, and also a digital twin at cell and process level developed by RWTH. All this is possible thanks to the workflow controller, which orchestrate all the tasks, and this was developed by CASC. But going a little bit more on details of each operation, so at the barcode station, we start with the article number detection. So the vision system automatically reads the article numbers on the label of the boxes, and this number is recognized, and thanks to it, we can go look into the product data repository of Masterly and to extract information regarding the detected item. Based on this information, we can understand if the box needs some manual activities and so needs to be redirected to the manual station, or if the box is ready for the robotic picking and so it can go to the robotic station. Regarding the robotic activity, it starts with the computation of the grasping points of the items to be picked by the vision system. And you can see in the bottom part of this slide some examples of the computed grasping point. Then the cobot moves to the computed grasping point. Here in this video, you can see some examples. The gripper can operate in 2 different modalities, with suction and with parallel grasping. For the parallel grasping video, I have blurred the part where the gripper open and close because this gripper is patent pending. Once we pick the items, we move them in front of an RFID reader to check the quantity of picked items, and then we release the picked item into the order box. And this is the end of the robotic picking process. Third activities, we have the manual activities. So the activities that are performed by the operators using the tablet HMI. Manual activities are required in 6 different situations. For example, if a product is not already known by the system, and so the operator needs to input its information into the tablet, then manual activity is required if the box is closed, and so needs to be manually opened by the operator. Or, for example, if the product needs to be ungrouped. So if we have to pick less product than the one in the group, then the robot will try the robotic picking for 3 times, but if it fails, then manual picking is required. And finally, if the automatic reading of the barcode of the boxes of the article number fails, then the box is taken to the operator for manual input of this information. Then there are 2 other activities which are performed in the background, let's say. We have a digital twin for real-time visualization of robot poses and of the camera views through RVs and ROS. And then we have the digital twin provides also a database of picking success and failures with saved pictures. And here in this slide on the right, you can see a screenshot of its user interface. And another process which is running in the background is the workflow controller, which is responsible for the real-time orchestration and monitoring of tasks. We have defined the 3 different workflows, one for each main station of the system. And when a box is detected in each position, then the workflow controller automatically triggers the corresponding workflow. The workflow controller directly communicates with all the subsystems of the solution, so the robot, the gripper, the database, and all the mastery modules. And in this slide, you can also see a screenshot of its UI when we can monitor the execution of the different tasks. And I think that was all from my side. Thank you for your attention, and I can give the floor to the next speaker.
Hello from my side. My name is Sotiris Aivaliotis, and I am a research engineer from a Laboratory for Manufacturing Systems and Automation from the University of Patras in Greece. In this presentation, we will go in more details on the second key exploitable result of Masterly, focused on the robotic mobile system for electrical cabinets assembly. So going more details, we will see here the current scenario that we are investigating as is right now before Masterly solution. So in the current version, the first operation that we are investigating is focused on the intra-shop floor logistics operations. The first step here is for the human operator to walk inside the warehouse area, then perform picking of assembly components box container to the assembly area, and finally deliver this box container with the assembly material to the corresponding assembly area. Then following on, we have the second operation, which centralized on the electrical components rails assembly and installation, as you can see also in the right figure. Here we have again 3 different steps. The first step is centralized on the read of electrical panels target configuration through an HMI. This comes with a form of a DXF file. Then we have the next step, which is centralized on the screwing of different rails and channels on the electrical panel. But finally, the picking and installation of different assembly components from the box container on the electrical panel. Currently, all these steps are performed manually by a human operator, as you can see in the right images. Following on, we have identified different needs which lead us to the designing of a masterly solution. The first need we have identified is that the human operators are performing currently repetitive tasks and need to be adapted to different and complex assembly configurations drawings. Right now, the operators see these drawings to the HMI and need to assemble different type of parts on the rails of an electrical panel. Additionally, as I said before, this assembly procedure and intralogistics is quite a manual operation, which cannot be optimized further in order to reduce the human ergonomics. Additionally, transportation and handling of different parts diversities is not a dynamic process, but quite predetermined. Focused on these needs, we have identified the scenario of a masterly solution. In this scenario, we are introducing two different mobile manipulators in the layout of the assembly workstation. So as you can see here right now in the image, we have in the right side the first operation. Here we have the introduction of the Coma mobile robot for the autonomous peak and in-time delivery of electrical components to the assembly station. The Command Mobile robot performs the pick and place tasks from the warehouse area to the assembly area. Then, in the assembly area, we have the introduction of another mobile robot, the RB Kairos, which is equipped with a UR10E robot. In this assembly area, the RB Kairos mobile robot and the human operator collaborate in order to assemble different electrical components rails on the electrical panels. In this assembly area, we have different modules and technologies implemented both from the human side but also from the robot side. From the robot side, we have the automated detection and in-hand manipulation and installation of different electrical components on rails using this RB Kairos mobile platform. From the human side, we have designed different human interfaces to support the operators during the assembly of task execution, as we will see in more details in the later slides. However, we have identified different challenges in order to develop this solution in Masterly. The first challenge that we have identified is that we have a wide variety of components to be assembled. We have a lot of components with different geometrical, size, and material characteristics. The second challenge is that we have different components which are placed inside the box container with a random position and orientation, as you can see in the middle figure. The accurate recognition of each part as well as its pose and orientation within the box is very critical for the automated pick and place of the electrical components from the robot. Finally, the third challenge that we have identified for the seamless human and robot collaboration is identification of the human presence and intentions by the robot in order to avoid any collision with the operator, but also the real-time robot's control to ensure the safe human-robot cooperation. In order to overcome these challenges, in Masterly we have developed different modules as you can see here. So we have performed the development of a flexible robotic arm, as you can see on the top right image. We have autonomous mobile robot platform developed also with the corresponding software solution for their autonomous navigation in the shop floor, as you can see on the bottom left figure. We have developed a dexterous gripper for rigid parts in order for the robot to be able to autonomously pick and place all the electrical components. We have solutions for the vision-based object geometry estimation, digital twin framework for mobile manipulators, as you can see on the top left figure. Additionally, we have software solutions for the dynamic task and actions planning, but also the workflow controller for the orchestration of the different tasks. We have an AR application for operator support and robot control, localization, motion planning, and collision avoidance algorithms, as well as AI vision and CAD-based robot programming for the robot in order to be able and autonomously navigate in the shop floor, pick and place different electrical parts from the box container. Additionally, as I said before, we have different software solutions for human tracking and human body collision avoidance from the robot side, but also different smart interfaces for human interaction with the machines. So if we can go to the next slide, here we can see the pre-industrial demonstrator that we have prepared at the TFCC premises. This demonstrator was very critical for us because we were able to validate in a pre-industrial environment all the modules of Masterly before transferring them to the real industrial environment. So as you can see here, we have the warehouse area with the Comau mobile robot, where the mobile robot of Comau is able to pick and place the box container with the electrical components. But also we have the assembly panel area where the human operator equipped with the HoloLens AR glasses, but also the RB mobile platform are able to collaborate in order to perform the assembly of the different parts on the electrical panel. Following on, we have here a short video with the results from the integration of all the modules at the Kliman premises in Kilkis, Greece. So we have the autonomous navigation of mobile manipulator of Comau in shared environments with human operators. But also we have the development of dynamic docking of mobile manipulators in order to perform the bin handling and the placement of the bin in the assembly station. In parallel, you can see the digital twin, where we have the real-time representation of the robot tasks execution. Additionally, we have developed different deep learning technologies for grasping points and 60 poses estimation in order for the robot to be able and understand in a precise way the location of the parts inside the box container. Using the result of this vision algorithm, the robot is able to approach the box container and pick different electrical components from the box container. Additionally, as you will see here, the robot is able to pick the part from the box container, and using some sensors that we have installed on the custom gripper, we are able to detect the exact pose of the part on the gripper. This is very critical for us in order to ensure the correct assembly of the parts on the rails and be sure that the robot has not failed the grasping of the parts. Additionally, we have force-based dynamic control of robots. As you can see here, we can receive force-related information from the robot, which is very critical for the correct execution of all robotic actions. We have developed AR-based interfaces for assembly guidance operators, but also through the AR application, we are able to perform the manual guidance of the robotic manipulator. So this is the different modules that we have developed in Masterly for the elevators manufacturing pilot. And with this slide, I will close my presentation. These are all the modules that we have developed and integrate, but also validate in the elevators manufacturing pilot at Kliman premises. Thank you very much for your attention, and I think that we can pass to the next presenter.
Hello, everybody. First of all, thank you for attending this webinar. As Elena said, my name is Carlos Tubio from Technique. I am research engineering, and I was in charge of the developments of the smart crane system for large material handling. Well, today I will present specially the smart crane system for large material handling, a key result from the Masterly project. This technology was developed to automate the movement of large aircraft parts in the Air Nova scenario. Well, here we can see the pre-Masterly scenario in Air Nova. We have on the left the scheme, and on the right the feature. The operation to move the scheme to feature is carried out with a special vacuum on a trolley to to move the skin to the feature. Mainly, there were two stages. First, the panel is moved from the trolley to the assembly area using vacuum gripper. Two operators are usually needed. One for the crane and one to guide the panel in order to avoid collision. The second stage focuses on the fine position of the panel in the assembly tool, the feature. This is more critical because very high accuracy is required. This is a pre-mastery scenario. All things are made manually. Well, needs. Always safety is the main priority. Always. It's mandatory. Well, also worker being reducing dangerous, repetitive, and tiring work for people. This makes job easier, safer, and less stressful for the operators. Another one, sorry for the typo, high precision. High precision proportioning of the skin in the feature. And the last, had autonomy, reducing manual workload through autonomous and safe movement. Challenge. High precision positioning of the skin in the feature. Also in the pre-mastery scenario, the load swing. Then we need a load sway suppression in order to avoid this case. Also moving the part automatically, avoiding collisions, of course, and efficiently generating and updating a 3D digital world in real time. In real time, because we need avoided collision and low sway. Solutions. Well, the proposed solutions were intelligent stationary feature for positioning the skin using advancing vision methods to achieve high precision. An anti-sway system to reduce the load sway generated during the crane motion. Sorry. High-speed collision detection for safety. Collision calculation should be made faster by using a simplified model of the load and efficient representation of the environment. Efficient crane navigation through 3D to 2D flattening. Planning directly in 3D can be too slow for large industrial environments as global facilities and may not always find a valid solution. Sorry. To simplify this process, the 3D world is converted in a 2D obstacle matrix for crane motion planning. And a digital world representation in an optimized data structure. The real environment is converted in a digital representation using efficient map structures, allowing faster road planning and safer autonomous movement. Well, in this presentation, we'll be focused on the smart crane system rather than intelligent stationary feature. Load sway analysis. Why does it progress? Well, we produce for crane acceleration, braking, and speed changes. Yeah, creating inertial force to create load oscillations. The load suspect behaves like a pendulum during crane motion, and the sway frequency mainly depends on the rope length. Based on the pendulum-like behavior, two control strategies were tested to reduce the excitation of the load. Notch filtering and input shaping strategies were evaluated as anti-sway solution. According to the test, two approaches can reduce the sway of the load when properly adjusted. For long and continuous trajectory, the notch filter showed better performance and reduced the sway from the crane motion. In the image on the left, the top graph shows the velocity profile, and the bottom graph shows the angle of the load. Here we can see the load swings during the moment and also after the crane stops. In the image on the right, the top graph shows the crane velocity after applying the notch filter, while the bottom graph shows that the load angle is reduced in a short time. Here we can see the difference between two graphics. Well, moving material with smart crane. To better understand how our system works, we can use Google Maps as an analogy. We need a real-time localization, fitting sensors on the crane. Google Map is a digital map of the real world. A planner. The planner along with the map is used to calculate the road. We need a controller to guide the car, and of course safety, brakes or radars or another kind of safety. Well, for the maps, we need perception sensors in order to understand the world. In the image on the left, we have a 3D sensor on the trolley. The image on the right shows a visualization of the point cloud of the 3D lasers. Here we have a good definition of the environment. Here we can see how the digital world is made. While the cranes move, the 2D sensors scan the factory floor. This data is used to create our digital map, allowing the system to know what the workshop looks like. I'm going to see you again. We can see the lasers. We can see a boxes, but it's a digital representation of the environment. Sorry. Well, now it's time to plan. The plan, as mentioned before, planning is a large 3D space, can be slow or sometimes doesn't find a valid path. Here we can see how to convert 3D world into 2D map in order to simplify the world and in this way plan more quickly. The process is the input is the 3D optomap and a height defined by the part. After that, in a loop for each X and Y position, we check if there is an occupied cell at that height. With this data, we create a matrix of free and occupied cells saved in a file. But the planner is not taking into account the skin size. Then we need to add a padding. for the world. The padding of the world is shown in blue here in order to take into account the part size. And after that, using a planner spline and knowing what is the destination, the planner can produce a route. For controller, our wheel path, the path is in a smart crane software on a PC, on a cabinet. This path is sent or writes on the PLC, and the PLC sends the trajectory, sends the set points to the motors, and monitors the position in order to follow the trajectory. Time for safety, checking the current world. For safety, the system checks the environment again after off-to-map, because the map may be out of date. The pipeline for the collision system is here. We have four modules. The first one is the 3D laser point cloud is filtered around the load. All the points outside the nearby of the load are not necessary. It's extra information. The point cloud is converted in Optomap, efficient representation of the world, which represent occupied space. The part is simplified using a simplified geometry. This is not a accuracy system of centimeters. It's just a safety but no precision system. This makes the distance calculation faster. FCL is a library to compute the minimum distance between the geometry and the occupied cells of the optomap. And the minimum distance is used to evaluate the clearance between the part and the nearby. If the minimum distance is below of the threshold, the system stops. Here you can see an example. The red box is a skin. The green boxes are the filter falls the interest area, and we calculate the minimum distance between the obstacles and the skin. We can see here an example with the skin and the column. That is just an example. And here we are how all the modules of the Nova scenario interact. The workflow control is the orchestration by means those action communicate with all of the modules of the Nova scenario. We can see the smart brake controller. After that, intelligent stationary feature move the skin to the fixture. Digital twin is of course a digital twin of the process. AR application for operator support assist to the operator in the process of moving the skin from the station to the intelligent stationary feature. A vision system based object geometry estimation and force-based control and handling. Well, future of the smart crane solutions. Techniker and HH will soon start a new project based on the results of the mastery project. HH Cranes have sold more than 100,000 cranes and 10 manufacturing plants. I think this is a good opportunity to follow the develops in order to improvement. Some improvements could be lower detection, the automatic calculation of the part size, because now the localization always is the same size. This which will allow the planner and then the collision system to be adapted automatically. Improve the anti-sway system, because sometimes reducing low sway can affect how well the crane follow the trajectory, and adding AI for people detection in order to avoid moving loads over people. Thank you for your attention.
So afternoon again. I'm Gabriele, as Elena was saying, I work in IIT, Istituto Italiano Tecnologia, and today I'm going to present you the work that we carried out in Masterly for designing modular gripper for handling rigid and flexible materials. Of course, you have already seen how this gripper has been used in the project, but today I'm going to give you a closer look at all the flow that led us, took us eventually to manufacturing this gripper. Inside the project in Masterly, IIT had the role of designing this smart mechatronic end effector. Problem is that usually when it comes to automating and using robot for grasping tasks, usually you need a dedicated tool that is characterized with very limited versatility and adaptability. So usually you have one gripper for one task. And conventionally, they don't adapt that well, and usually the majority of grippers are fit and designed for holding and handling rigid components. They usually fail when it comes to picking soft objects. This is because the deformable objects undergo this, deformation when the fingers are applied. That's why usually you go with soft fingers, like the Gorilla gripper that you can see here in the top right corner, but these kind of gripper don't behave that well when it comes to picking hard and rigid components. Usually these grippers are in open loop, so there are no feedbacks, the sensors applied are very limited, and they're not modular, so you cannot switch and combine the grasping principles. We approached this project in collaboration with STAM and Decathlon, of course, and we needed first to overcome these limitations and come up with a solution that could be a perfect match, a good fit with all the needs that Decathlon highlighted. Francesca showed you the high variety of products that Decathlon work with. So we had to come up with a solution that could adapt quickly to rigid and soft or deformable objects. And we didn't want to go with a finger changing tool because it would have taken a lot of time. So we had to deal with objects and products made of different components, some of which could have been delicate, others were totally rigid, and we needed to come up with a solution that was pretty flexible. The Decathlon warehouse are characterized by a high mix production. So we had to deal with different products and components. And of course, we had to build something that was reliable and could give a consistent and reliable grasp when applied to all the products that they have in the warehouse. And most importantly, we didn't constrain and we didn't limit the size of the object that we had to pick up. So there were some backpacks that were flat, so wide surface, but mainly 2D, while we had to grasp also some basketballs that were totally 3D and a different size, but also very small boxes. So coming up with a solution that could merge and match all these needs was not an easy task. That's why we decided to build and to design a robotic solution that could put all these features together. And we wanted to design a gripper, a device, and an effector that could be sensorized, so it could adapt to the shape of the object, and it could deal with soft and rigid object at the same time. We wanted, in this case, to design fingers that had 2 degrees of freedom. In this case, they could host and surround the target and accommodate the target in a safe grasp, but also something that was smart enough to switch and to identify the best grasping selection according to the target, and could fit usually cobots. So the design had to be compact. Here on the right hand side, you can see a picture of one of the first design of the gripper that we can come up with. So as you can see, the fingers are equipped with sensors, but also we thought about installing one proximity sensor also in the palm of the fingers. In this way, we could have an additional feedback about the position of the object to grasp. Unfortunately, of course, we faced a lot of different challenges. Like, for example, the electronics was not trivial, because when we had to install different sensors in the fingers, and in this way, the wiring was not an easy solution to come up with, because the wires could have hindered the picking of the components, because we're talking about, Francesca showed us that we had to deal with box full of different objects, and we had to shield the different wires for preventing interference and having a clear signal to drive the control of the fingers. And also, we had to install switches and electronic devices that could ensure that the positioning of the fingers was reliable and always repeatable. Identifying the different tools, the different sensors was not easy as well. And to overcome all these problems, we had to come up, we had to identify specific solutions for every problem. So eventually we managed to design and implement a self-calibration routine. So in this case, we made sure that the fingers were opening and closing always in the same position, and they could run the command that the operator was running. Also, we installed inside the fingers and in the fingertips some suction cups. So in this way, we could strengthen the pickup, and the cups are now controlled independently. And also, we managed to fuse the signal coming from the different proximity sensors in the fingers and the fingertips. In this way, the fingers can autonomously adapt and adjust the distance to host and to safely hold the different object. Now, the final solution is in this picture on the right. Unfortunately, I cannot disclose too much technical details because we recently submitted the request for the form for patenting our solution. You already seen in Francesca's presentation some videos, and also in those ones, I'm sorry for that. The gripper was blurred, but we need to wait a few weeks before hopefully we can release and disclose this information. But just to sum up, we designed a gripper that has 2 paired degrees of freedom in the fingers. It's equipped also with suction cups on the internal side of the fingers and the fingertips. It's equipped as well with proximity sensors, so we can close the loop in the control of the fingers, and also can be installed and mounted on cobots of different manufacturers. You already seen a video showing how the gripper works, but just to briefly I didn't change the slide, sorry, there was a mistake. Basically, the vision pipeline that has been developed points and identifies the grasping points on the target objects. The gripper is driven in position, and then according to the type of object, the gripper switches into the right mode to pick it up, and then we use the proximity sensors to prevent slipping, and so we can adjust the fingers, and then the object is safely grasped and then handled and released. Again, I'm super sorry I cannot show you and give you more technical details, but if you want, please feel free to reach out to me so we can try to arrange a one-to-one conversation, and I'll try to give you some more information, or once the patent is hopefully accepted, we can release all the information that you need. Thank you very much. I think we can pass to the next speaker.
Yes, hello again from my side. In this presentation, we will go in more details in another exploitable result of Masterly, entitled AR application for human operators support and robot control. So starting with, we can check in this presentation, in this slide, the different needs that we have identified and led us in the designing of this AR application. So initially we have identified that the operators in the industrial environment were in need of support related to the conditions by providing real-time guidelines and recommendations to them. Additionally, we have identified the need for quick and easy training of inexperienced operators in new manufacturing operations. Third, in human-robot collaboration, we need higher operator awareness and safety, as the operator must know what the robot is doing and stay protected. Then we have the interaction with the production system, which has to be hands-free and seamless for the operator. And finally, the operators needs an easy way to manually control and reprogram both static and mobile robots without expert tools or programming knowledge. So all this resulted to the definition of the solution of the AR application that we have developed. As you can see here, we have identified this application as an augmented reality application to enable seamless human operator support by providing real-time instructions, notification, and indications related to the ongoing operation status and the operator needs. Additionally, we have specific functionalities integrated in the application in order to allow the communication with the production orchestration system, as well as the communication and control of robotic operators. This application runs in HoloLens 2 device linked with the central orchestrator of the production for operator support. Additionally, we have step-by-step holographic guidance based on CAD holograms, but also virtual hand guidance. We have also developed an AI-based vision software for handled parts detection using the augmented reality glasses camera, but also an LSTM-based module for the auto-completion of human tasks using IMU acceleration data. This is very critical because we have seen that we can reduce by far the cycle time of the production in our case. Then we have the provision of real-time alarms like the max force applied and robots' future trajectory visualization to human operators inside the virtual world of the AR glasses. Additionally, through the AR application, the operators can pause or resume the execution of the assembly schedule, but also reprogramming of robots in a safely way using holograms. In the image here, you can see through the camera of the AR glasses how we can identify the part that the operator handles and accordingly update the holograms in the AR application. Then in the next slide, we have the different challenges that we have faced during the designing of the application, but also its implementation. Firstly, we have the need for the accurate calibration of the holograms, because it's very critical for the operator in the virtual world of the application to see the holograms in the correct location inside the virtual world. Additionally, we have identified the challenge for a reliable real-time connection between the AR application, the workflow controller, which in our case is the central orchestrator, but also the robot resources. This real-time connection is very important for us in order for the operators to have more a good interaction with the resources in the assembly scenario. Then we have tasks completion, the automated detection of them without burdening the operator with extra messages which can be off from their side. Then we have the challenge to convert Unity to ROS2 coordinates. Unity is the platform that we have used for the development of the AR application, and it was very important to have the correct conversation of the coordinates between the ROS2 and the Unity in order for the operator to be able and have precise the robot goals. Finally, it was very challenged to create an AR application for both experienced and inexperienced operators across the 3 pilots of Master. Then, based on these challenges, we were able to create the final solution for the Masterly project. So we have developed a holographic user interface with a guided calibration procedure, interactive send goal holograms for the operator in order to be able and create in more accurate goals for both static and mobile robots, as you can see also in this image. We have developed an AI-based vision solution for part detection, but also an LSTM-based module for the auto-completion of the tasks using acceleration data from an IMU sensor, which is handled by the operator, as we will see also in more details in the next slides, but also the future trajectory visualization inside the visual world of the application, and the pause and stop of the operation execution for the safe intervention. In this slide, we will see in more details the architecture that we have designed for the implementation of this AR application. So from the operator side, we have 2 different sensors. We have the AR glasses, the Microsoft HoloLens 2, which is used to run the AR application, but we have also an IMU sensor, which is hand-worn from the operator side, and provides real-time data acceleration data from the operator's hand. All this information is transferred to the ROS2 middleware using TCP and WebSocket bridges in order to be then transferred and used by the perception and AI-based software modules. In more details, the AI vision module using the AR glasses camera for handled parts detection, but also the software solution for the auto-completion of the human-assigned tasks. All this information is then transferred to the workflow controller, which is the process orchestrator and execution manager. And from the workflow controller, the corresponding commands are sent to the robot controllers, like the UR10E arm, but also the Comau and the RB Kairos mobile robots for their behavior adaptation. In the next 2 slides, we will go in more details on the different functionalities that we have developed inside the AR application. Starting with, we have the provision of hologram-based instructions to the human operator regarding the correct and accurate position of the different electrical parts in the electrical panel. Additionally, we have the assembly instructions provision using text information, as you can see on the top middle figure, but we have also a small figure of the physical part in order for the operator to have the whole information needed. Also in terms of the aeronautic pilot, it was needed to have a notification about max force limit exceeded, as you can see on the top right image. We also have robot guidance instructions to the human operator using hand images holograms inside the virtual world of the application, but also different procedures for the human operator in order to program both mobile and static robots. As you can see on the bottom right image, we can see here how the operator is able to interact with the tool of the robot, and using the hologram of the robot create new poses for the robot as goals. In the next slide, we can go in more details on the programming of both mobile and static robots. So, as you can see on the top left image, this is what the operator sees during the execution of a new robot motion. On the middle top image, you can see how the operator is able to create new commands for mobile robots. So using a hologram of the mobile robots, the operator is able to create new poses, but also use interactive buttons of the AR application in order to send the corresponding goal command to the robot controller. Additionally, we have created a feature inside the AR application for the human operator to be able and give directly a command to each robot's joint. So as you can see on the top right image, the operator is able to give direct values to the different joints of the UR10 robot in this case. Finally, as you can see on the top, on the bottom right image, we have the integration of the LSTM model for parts assembly. So as you can see here, the operator wears the IMU sensor. This IMU sensor records acceleration data during the assembly execution, and this data can be used by the software that we have developed in order to detect the completion of the assembly task by the human operator. So in this slide, you can see that the AR application has been successfully integrated and validated in the two pilots of Masterly, the Kliman and the Aernova 1, as we have also seen in more details in the corresponding CARES presentations before. With this slide, we can conclude my presentation for